Good afternoon, everyone, and welcome to our exciting webinar on boosting efficiency and digitalizing the production of composite parts. I'm Benjamin Debucher, Head of Events Program for JEC, and I'm thrilled to have you all here with us today. In collaboration with sensXPERT, we have organized this webinar to address the challenges faced by the composites industry in producing high-quality functional parts through complex and unpredictable processes. The aim of the webinar is to shed light on the benefits of digitization using sensor-based and data-driven technology, as demonstrated by an aerospace company's successful implementation of these strategies. During this webinar, we will explore the challenges in composites aircraft manufacturing. We will talk about gathering data with sensXPERT in mold sensors. We'll present in mold dielectric analysis. And last but not least, we'll discuss the digitalization of composite components. For those unfamiliar with sensXPERT, sensXPERT is a leading data-driven manufacturing solution for the plastics industries. And the webinar today will be presented by two esteemed data scientists at sensXPERT, Dr. Phil Gralla and Dr. John Puentes. Phil's expertise lies in algorithm development, particularly in the field of image processing and the sensXPERT digital mold and pipe solution. And John, with a background in mechanical engineering and material science, brings extensive knowledge in CNC, polymer, and composite manufacturing, as well as machine learning algorithms to the sensXPERT team. Throughout the webinar, please feel free to ask your question to Phil and John using the dedicated tab on your screen that you will find at the bottom right next to the chat tab. And don't forget also to participate in the 3 polls that will appear during the webinar to share your goals and preferences. We will address all the questions that you have asked during the Q&A session after the presentation of Phil and John. Now let's dive into the world of boosting efficiency and digitalizing composite part production. I hand the stage over to Phil and John. Thank you.
Hi, Benjamin. On behalf of the sensXPERT team, thank you so much for having us today. We are really excited to gather here with a really wide group of within the composites community. The case study today is the aircraft industry, but we will see at the end that our technology applies to many different fields. I'm John Puentes. You see on my screen my colleague Phil. So we'll walk you through the different steps of the presentation. So as Benjamin mentioned, within the agenda today, let's just divide it in like 4 different components. First, let's focus on the challenges that we are facing in the composites industry. Then let us walk through the technology of sensXPERT. Of course, one of the important elements is the physical part, which is dielectrics. So we will do a review for some of you. For others, it will be a learning opportunity. And then Phil will walk you through how digitalization can improve and optimize your processes. Within this particular presentation, we will focus on composites, and then we will focus on the aircraft industry. So every time that we discuss this with customers, there is a key element. It's usually a financial element. But this financial element has different elements, right? Let's start with the technical element, process stability. We really want to understand what is happening with our material. The material has different changes from the moment our material supplier transports it, right? From the moment we store it, from the moment we thaw the material in case it's in the fridge, until it goes in the mold. Aging. There are many changes that in regular quality control systems, we are not including. The second challenge is transparency, as you can see here. And within this, I will say that for most of us in processing, the mold, what happens inside the mold with the part is a black box. So within this black box, what we hope to do is to give you an open window, and within this open window, we're gonna, it's a really wide window, but we are trying to give you what are the critical parameters that can help you in the manufacturing process, and what is really happening with materials, what is happening with the composite. In most cases, we are working with a thermosetting composite, so we will have these transitions, chemical, physical, from liquid, gelation, solid. Then we got to another element that is not so much technical, but is more sustainability is something that is affecting our personal lives and professional lives. There are, as you can see in the slide, there are a lot of different cases where this is coming to regulation. One case that is the EU Green Deal. So in the future, we're going to face, or not just in the future, but currently we will be facing this classification of companies between sustainable practices, non-sustainable practices, and this will be linked to different financial issues, such as getting the proper loan from an institution to pursue our projects. And at the same time, within the last item that we see, item number 4, just linking all this financial benefit. Now we have technical aspects, we have regulation aspects. Now, most of you out there, engineers or somebody in the plant, will want to reduce scrap. Scrap is a big component within, despite all the knowledge that we have in composites, scrap continues to be a big target. And now that we cover this idea within the composites manufacturing, I will give it to Benjamin.
Thank you very much, John. And it's now time to answer the first poll of this webinar with the question, what is the main area where you try to optimize aircraft applications? So please answer this poll by choosing one of the answer or multiple answers. So process stability, gaining transparency, sustainable practice, reducing scrap, or others, and in this case, please specify your choice in the chat tab. So let's see the first result that we have. So for the moment, for 40% of the audience, it's more about sustainable practices. And process stability, it's evolving a bit. So process stability for 42%, sustainable practice for 36%, reducing scrap for 18%, and 5% for other. And no one answer gaining transparency. Yes, one now, so 4%. Thank you very much for your answer.
Right, thank you, Benjamin. So I will take it from here. Also, hello from my side, and welcome to this webinar. Very interesting, I have to admit. I was expecting the scrap to be on top, but yeah, process stability and of course sustainable practice is a very large topic, and we notice it's coming up a lot more than before. And so we are happy to dive into the topic, how can we help with this one? So let's have a look first on what we are actually doing and how we gathering data. And why are we gathering data? How can we do it? The sensXPERT itself is coming from a bigger company. We call it now something happened. Yeah. So we coming from the NETCH. Right. Okay. So sensXPERT is a brand from the NETCH Process Intelligence company, and we are actually we founded 2 years ago, and we have another company, NETCH. So it's a larger company and has more than 50 years of experience in material science and sensor technology. Some people from you might already know this company for its analyzing and testing for the machines. And before, we always had like material before the production or after parts were manufactured. We had some samples, we tested it, and we have some more insights. The idea was we would like to have some way to incorporate our knowledge and our measurements inside the molds, so doing the process directly. And that's where sensXPERT was founded and where we started working with. So while we are still a young company, we're actually coming with a lot of knowledge and a lot of backup in this area. So for the change that we want to do is we actually, what we're doing is we have our sensors and we can directly look into the process. So we can install it, it's going to be installed into the molds where it has access to the material while the production. And then we have the small IPC there. It's going to take all the information that's coming from the sensor and stores it. What are we going to do then? Well, we will analyze this data using machine learning mostly to give feedback about process. Is everything going accordingly? Is there some change? Can we predict already that this part is going to be good or bad? And so this data is being processed directly on the IPC. And in the next step, we will send this one to give some feedback to actually the engineer. So it can be accessed via some web application to have live graphs and live data. And then the engineer manually or later, if they like, automatically can already make changes in the production. At the same time, we're also going to take data and store it in the cloud. The idea is if you have multiple processes or also timelines, that it is stored, it can be accessed. You can compare your data to like other machines that you have if there are something ongoing. We can also use the micro data to work with it, to improve the models and also to gain more insight about your own production. Again, this one then is also being accessible via a web application. And you can customize your dashboard to have some ideas of your data. You can select different graphs. You can customize it to your needs so that you have the information ready at hand that you need. Right. So now, one thing that we always do is, of course, we have our large data. How can we work with it? And that's where the machine learning is coming, because you're not going to use machine learning on the small device, but instead we're going to train everything in the cloud and then have it locally running in your local machine so that we can access all the data and we can make the best models that we have for different processes and then only use the model for the prediction on the IPC. So you don't need web access while you do production, and you can only upload data at certain times. And the cloud service that we have, you can also then, of course, access from everywhere. You have access for 24/7. You have our process data transparency so that you know what we're doing with your data, which data we're actually processing. And you can also download the data by yourself and just have a look at it. So some companies would also want to do their own data analysis, so you're also able to do that by just downloading data and use by yourself. So,
thank you.
And with this short overview about our technology, we would like to tell you a little bit more about how we're measuring and what we're measuring. And John, please take over.
Before we move on to John, Phil, I have a quick question I'd like to ask you on this part. Can the process be adapted to control the machine? Hello? Phil, can you hear me? Hello?
Phil, can you hear us?
Can you hear us, Phil? Oh, okay.
I'll fill in for Phil in the meantime, Benjamin.
Yes. So let's move on to the. Yeah.
So for now, yeah, that's what we saw, right? Like we have the answer is yes in the long term. It will be specific to each like customer need, but eventually, as you can see, we have the hardware element. We also have the software component. And our hope is that as there is one interface for the person responsible for the production, whether it be the technician, whether it be the engineer, you have the web app interface. Um, there will be some sort of like trigger alarm or like warning where the data is deviating for the standard. And then within your company, where the technician or quality control can take action. Right? So that's a little bit of yeah, one of the great things that we can do.
Okay, thank you very much, John. Maybe let's move on the second poll for our audience. So I'm publishing the poll right now for the audience. So what technique do you use for quality control in your process and experiment? So you can choose ultrasound testing, DSC post-cure, DMA post-cure, dielectrics, or others. And again, please specify your answer in the chat tab, please. So it's time to answer. So for the moment, it's more ultrasound testing for 35%, and then equal DSC post-cure and DMA post-cure with about a bit more than 20%, dielectrics for 11%, and others for 5%. Please don't forget to specify your answer in the chat tab. Okay. So yeah, ultrasound testing for 40%, and then DSC for 25%, and then DMA for 19%, dielectrics for 10s. Let's move on to the next slide. Phil, if you can hear us. Hello.
We might have a small technical problem with Phil, but it should be resolved quite soon.
Yeah.
I will say in the meantime, I've been in the field before. I have worked with all four methods. I was expecting. I knew that the mechanical testing within the aircraft industry, ultrasound will be one of the leads. I was quite expecting a little bit more of a DSC or DMA there, but and it's great to hear that 11% of our audience is already familiar with the dielectric analysis. So for those of you, this may be a review. For others, it will be a learning opportunity. So far to recap, we started the presentation by covering the challenges, right? We saw the four pillars. It seems that within our audience, we have process stability and sustainable practices. Then Phil walked us through the sensXPERT technology, where we have the hardware. We also have the software element. And the interesting part of like eventually you will be able to do the quality control. Now to explain the physical principle behind the measurement device, let's dig into dielectrics. I think we lost Phil, am I right?
Phil is back.
Okay.
Phil, can you reshare the presentation if you hear us?
As always, you prepare for all these issues, but it continues happening. So let's as we continue getting Phil back on track.
Yeah. Here it is.
Perfect. Okay. So back into dielectrics. For all of us here within the composites industry, let's take the easiest way to understand the concept and how our sensors work is by assuming that the polymer or the composite material is going to be a medium within a capacitor. So as you see in the two figures here, let's assume the simplest case scenario for a capacitor, a parallel plate one, where these two plates are electrodes with opposites. So we are gonna expose the material to an electrical field. In this case, what we do is we send an alternate voltage, right? And within the material, uh, within the polymer itself, there are there will be an ion motion. So there are some elements like the dipoles and the charge carriers. All this means that the reactivity of the material and some of the chemical components are making this motion into the ion mobility. So logically, these dipoles will try to go towards the opposite electrode, the electrode that has the opposite sign. So we are going to have this rotation and motion as we are measuring. So in reality, what we are measuring is the motion of these dipoles. And as you can imagine, this material is going to undergo physical and chemical irreversible transformations. So we will have a liquid light, gelation, and solid. Eventually, as the material is solidly defined, it's going to become more difficult for this. The motion is going to be hindered. It's going to become more difficult. And this is what our sensor captures. In the next slide, we'll see how we can take this theory into practice. The traditional way to use dielectrics is in a lab setting. You have here on the left the traditional parallel plates. So you have the two electrodes. You have the medium within, and then the polymer is exposed to this electric field. But this is a little unrealistic for the production setting in our industry. So one of the ideas that we have is, okay, let's keep the electrodes in the same surface, in the same plate, and then alternate the different these different electrodes, producing a different signal that travels through the material. But once this idea was finalized, then we have a proprietary sensXPERT sensor. As you can see on the right, this sensor, it's basically the same component. The black circle that you see here is the inner electrode. The outer shell will behave as the second electrode, and since this is connected to a metal mold, the mold itself will become an electrode within the system. And what we are measuring is this: what is happening with this with the current. So we send the voltage, right? The alternate voltage. Of course, we get a phase angle, we get a current. So what is happening with this signal as the material is undergoing all these chemical, all these physical transformations? Another interesting thing to notice in this sensor, you can see a ring. So sometimes we measure very liquid systems. So we make sure that there will be no leaks within the system, and a thread-like, so it's very easy to implement within your molds. On the next, we will see how this translates. When we are using dielectrics with the sensor that we just mentioned, then in reality we are measuring two things: resistivity, and this resistivity has to do with energy loss in the material. And then we measure permittivity, and this is related to energy storage. Most of you in the mechanical field are familiar with a storage loss modulus, right? DMA rheology. So here the resistivity is very analogous to the mechanical viscosity. So here we're gonna label the resistivity ion viscosity. As you can see in the plot, what happens with our sensors between 0.1, 2, and 3 looks like a viscosity curve. After that, it's more like a solid behavior. So what we can measure within this sensor, you see here a typical example of an RTM resin. We have the dynamic isothermal heating cycle, and within 1, we start detecting the material. Then in point number 2, as the chemical reaction progresses and the temperature increases, we reach the minimum viscous point. For infusions, this is really important. We want to know this time to make sure that our part reaches the end of our mold. For per preg, not so relevant. Then by point 3, we are reaching the gelation level, but we no longer stop there. We can actually continue, like a rheometer would stop there. And then we will have to switch to, for example, a DMA. But here we continue, And we can see that in number 4, as we are reaching the plateau, this is what we will imply the solidification, the final solidification phase. And of course, for most of us, trying to interpret this data or in terms of dielectric variables will be a little challenging. So the easiest way is to translate this into a language that we know, which is the degree of cure. You can see here now the new green curve. Let's assume that the reactivity between 1 and 2 was very low. Then let's assume that at 2 we can start calculating the cure. And we see how the material is progressing from this liquid-like until the solid stage. In the next one, just to wrap up this, we have a sensor that is designed for the manufacturing environment. It's been tested for, as you can see here, for several materials, a wide range of thermosets. And for most of you here, we are covering composites, right? Which is like woven fiber. Then within the processes, we are familiar with prepregs. We are from prepreg processes, transfer molding, all the variations of transfer molding, and any vacuum infusion as well, and the post-curing in autoclave. Depending on the case study that you have for the different problem, we can target this solution to perhaps degree of cure. If you're interested in the mechanical part, the glass transition temperature. And there are some additional things that one can do with the electrics, such as measuring mixing ratios, problems within the system, aging through the history of transportation of the material, and so on. Now, let's put this information into a context, into a case study of one of our customers. So here, the process was vacuum-assisted resin transfer molding. Most of you might be familiar with that process. Of course, usually this is coupled with a post-cure, and this is done in an autoclave for the aircraft industry. And we're just gonna name a fuselage support as an example of a part. Now, the image that you see here, of course, is not a part of our customers' inventory, but this is just to give you an example of any composite part that most of you might be producing. You see the complexity. There are different fibers, fiberglass. You have carbon fiber, and with this carbon fiber, you have different orientations within the part to make sure that the stresses that this is going to withstand are fulfilled. And also, most likely, this is going to be an epoxy system. So here, what we are going to discuss today is a case study with our customer with a woven carbon fiber. Most of you are familiar with the RTM6 by Hexel, and it's RTM6-1 because the two components are mixed. So we have to keep this resin store, and this can be problematic due to aging. One of the criteria is after transfer molding, when do we reach 80%? Can I actually optimize my cycle time? So this was the main challenge within this process. It's a well-established process, but we wanted to push it further and optimize it. So just to recap, multi-stages will go through infusion, then compressing in a transfer molding system. Then the part has to be cooled down. Then we do a post-cure in an autoclave. And this might be familiar to many of you. In the aircraft industry, we are not in the business of quantity, but big parts and really high quality. So the cycle times are usually very long to avoid residual stresses as you manufacture. There is usually limited data because these parts have to go through many stages. So then maybe not all departments have the right documentation. And most likely this material is going to be non-homogeneous. So in different locations, you're going to have different material properties. So the challenge of our customer here was, can we digitalize this process to make sure that we have a fingerprint of every part. At the moment, it's not possible to do testing of every single part in every single stage. So is it possible to digitalize it? If this is possible, this will give them a lot of transparency. So after the part is made in the manufacturing department, then they can give this transparency to the next department that most likely is gonna do some surface finishing, some painting, maybe adding some holes within this fuselage support. Um, Obviously, once we have these two things, we can optimize the cycle. And the biggest challenge is, can we forecast the degree of cure even before the part is done molding? Uh, Within all this, they hope to reduce scrap, and they hope to become one of the leads in sustainable practices, which is one of the priorities for our audience today. Now, of course, we have dielectrics, but most of you are familiar either with mechanical testing or with thermochemical testing, TSC. Here, what I'm showing you is one of the first principles that our technology uses. The entry point, like one of the data entries, is what you see here is a kinetic model. This was most likely taken in a DSC. What you see here is like different heating rates. So we have different exothermal reactions, enthalpies, and mathematically, we can translate these enthalpies, this energy release, into a degree of cure. From the zero liquid light stage all the way to the theoretical 100%. And here, this was another interesting part. As you can see in the upper right side, our customer today does post-quality control. So you go through all the 3 stages, right? Which is a very long process. And then you might have quality after the fact. But what we did within this case study was, can we actually open the mold and then just give them a hint of what is happening? And do we have to measure every single stage, or can we just measure part of the stage and then visualize the whole process?
John, I have a quick question about this part. Sorry to interrupt. I'd like to know how is the modeling done, and do you use any commercial software or any other tools such as FEA, for example?
Oh, that's a great question. So there is always the coupling when we have quality control. So most likely your company is doing quality control before we mold, quality control post molding, and a lot of the times we try to do simulation in finite element analysis. For now, this is not our case, but we can use our technology to be coupled with finite element analysis to go even further and do analysis of mechanical properties, flowability. So what we use, which you see the title already, Phil will walk us through, is we are using machine learning algorithms that take physical principles um, to produce a solution. So it's a proprietary, and we are not using at the moment a commercial software.
Okay, thank you.
Okay, I hope everyone can hear me. I'm very sorry, in between my headset broke. Yeah, okay, I see.
We can hear you.
Everything's fine. Then I will take over now again for the machine learning part. So first, let's do a poll. And I would like to know a little bit, from you, Benjamin.
Here is the third and last poll of this webinar. So are you using machine learning in your production facilities already? So you can answer yes for quality control and process control. We use it for a few specific tasks. We are in the process of developing machine learning-based solution for our processes. No, we don't use it, or no, we don't use and don't have the expertise to develop our own machine learning-based solutions. So thank you for answering this poll, and let's see the results. So most of the audience don't use it for 40%, followed by we are in the process of developing machine learning based solution for our processes at 25%. Then at 20%, they don't use it and don't have the expertise to develop it. and 10% for quality control and process control.
All right, thank you very much. So I can see there is already starting a little group using it and some more interested. However, since there's a larger group who might not be so familiar with the topic, let's have a quick overview what machine learning is, and then we can go more into the specific details for what we did for this customer that John was already talking about. So for the machine learning, just very broad overview, I call it machine learning onion. So we have the very broad term AI, artificial intelligence, and this is just a wide spectrum. And one part of artificial intelligence is the machine learning. So it's part of this one. And an even smaller part, so a very specific type of machine learning is the deep learning. That's the most popular one currently. Very famous for ChatGPT, for example, using deep learning. And just, I would say the last 10 years since 2012, got a lot of traction. And with it, actually also a lot more machine learning applications.
And a quick question on this slide, Phil. Do you have an example where artificial intelligence exists without machine learning?
Yes, so actually the artificial intelligence is possible without machine learning, so without learning something. And one of the typical examples we see is swarm intelligence. So sometimes very simple rules like game of life or also the little robots, sorting robots, they have a hard-coded behavior and they don't react, they don't learn, but they are still performing very complex tasks. And this one would already count as artificial intelligence, although there is no active learning involved. Now, for us, interest why we focus so much on the machine learning part, and the reason is here. So when we are talking about AI or also automatic processes, what we had before is always in the classic approach, we have some type of data coming in, and we take our data and we need an algorithm that works with data, crunches it, that changes it, that extracts some information. And the classic approach would be that you have an expert in the field and in programming that is able to translate this human idea of what we have to do with the data into the program to always generate an output, which of course is still feasible. And the change that we have now with machine learning is that we don't need to specifically train write this one algorithm, but instead we make something which is also called meta programming. So we don't program the algorithm to tell exactly what it's doing, but we have algorithms that are able to adapt and learn from data that we provide to them first to be able to solve a task. The advantage is a lot of times it's very difficult for us to specifically tell a machine how we interpret data, how we work. So the more complex it is, the more difficult it is for us to tell a program what it is. Like on an image to tell this one is a human. Describing a human to a machine is very difficult. But we can instead have a program that is able to take data, information, and also our information saying like here we have a lot of images and these ones are humans and these ones are cats. And it can learn to adapt to distinguish between these two. And then we can apply it into our process. And yeah, so two key advantages. One is we can now solve very difficult tasks that is complex for us to understand, like to teach a computer to tell how it works. And the other part is we're actually able to transfer knowledge from one process to the other. So we shifted our expertise away that we need someone who can program and knows very well what the data is to someone who can work in general with data and computers and is able to faster understand and apply his knowledge to a different process. And this is the advantage why there's also a lot more machine learning coming. And for us, I already said before, deep learning is one part of machine learning. It's not everything. And so deep learning, the neural networks is one very well-known technology, but it's not the only method. And there's a couple other ones. So we have the neural networks, we have support vector machines, gradient boosting with tree, or k-nearest neighbor. So these ones are some of the methods that are still applied nowadays, and each of them has specific advantages and disadvantages. So depending on the customer and depending on the data at hand, it might not always be the best choice to go with deep learning. Sometimes something like gradient boost or also support vector machine is the better choice depending on the data that you have. And that's exactly the case that we have with our customer, because before, most times we try and we use deep learning, but we had the issue, as we said before, we have very long cycles, we have very few data, and we have a lot of changes because it's still like the process still being set up and things. So we don't have enough to actually do deep learning. And that's why we had to choose a different method, the support vector machines. But why did we find it out? How did we find this one out? And we have something, and here we call always our data science life cycle. So the center of my work, and also one from John, is of course the data, the thing that we get from the sensor. And if we have a new project, a customer, we always have this circle of life that we have to go. We start at the very top, and still, of course, we need to understand the process at hand. So we need to know what is the material that's being used. We have to understand what is the goal. Is it really just scrap reduction? Is it something cycle time reduction? Is it forecasting? Is it gaining more insights? Is it changing maybe the material, being a process that's unstable to see if we can increase the stability? All these kinds of things is important. The other part is these process dependencies. That's something that we will see later. So a lot of times we do things and the customer do things that we might not be aware of are important. So we need to understand this one and tell what you're doing here is important, or maybe you have an extra step that's not necessary. If we have this one and understand the process better, we can have a look at the data. So we need some understanding of our data, also some visualization, so that we can already show, okay, we get this one, we can find something in the data. What can we actually measure? Is it possible to see, like, in some process, some changes? And if we have done that, if we understand what we're actually collecting, we always go into the data preparation. Data preparation means we need to select features, we need to look which frequencies we are going to measuring. Do we have extra sensors we can use? Is there some kind of outliers or something in the data that's not supposed to be there? Remove this one, work with it, and now we have something we can actually feed in the model. So we're not just taking data and dump it in. So we only want to take meaningful insights for our model. Then the modeling happens. So we select from the appropriate architecture, from the appropriate inputs, can train on the one. And after we have trained it, we also evaluate the model. How is it doing? Is it possible to solve our goal? If we only train on part of the data and leave the other one out, are we able to translate what is trained to this unknown data set? That's always important because later we want to use it in production. Of course, there we also need to make some visualization. We need to have some communications to already explain what we're doing and also analyze the results. When we have done all these steps and are satisfied, then we will come to the deployment. So now we're gonna have it locally installed on the IPC. We're gonna have a customer-based model so that you can choose one that's specifically for you, and also have some model monitoring. Is something happening over time? Do we retrain as new machines coming inside? Can we access more data? And important is always customer feedback. So of course we need to know, is everything right? Maybe the customer also would like to change something. So in all these steps, even though it's only the last one, the customer is somehow included and also make transparent what we're actually doing right now, so he understands what is our goal. Yeah, so for our case in the aviation, we had a very specific problem. And let me show first what this one was, like how the result is, and then we look at our issue. Because we had to not only simulate, so we wanted to understand, we wanted to know what happens if I change certain parameters, but also optimize. And when we were there, this is our solution. So the blue one, that's the target value. That is after we observed the whole process, we know how it's going to behave in the future. Until this black dashed line is how far we already know data, so how far the process is. And then we have these dotted blue, like turquoise line. This one is telling us our prediction. So we want to know beforehand, how is it going to behave in the next steps? How is it going to behave in time? And we can see, of course, the longer we observe a process, the better we are at predicting how is it going to behave in the next time. And this prediction is made with AI. So we use our model, not deep learning, but the support vector machine. And of course, you could also use this information to control the process. If you can see, oh, I'm not going to hit my target degree of cure of 80, maybe I need to do something else. Maybe I have to add something. Maybe I should increase my temperature. Maybe I should keep it longer in the autoclave or something, so that you know already at which step what is going to happen, and then you have time to actually adapt it. And the problem we had is actually, so we had to combine our simulation and measurements, because when I got the measurements the first time, they always stopped after like 2 hours. And the degree of cure was way too low. So when we came to visit the customer, they showed us that after the molding step, they actually left the part in the mold, took it out, disconnected the sensors, but left it there for 10 hours. So in this time, the mold is slowly like cooling down. That's what we call it, cooling down phase, but it still has a lot of energy that goes into the material. So there was curing happening outside of the VARTM or the autoclave. And that was an important step, because before we only had the other 2 steps, and we said, that can't be, we always way too low. So we noticed that one and we said, okay, what do? We have only a few cycles. We would like to use this one to train our model. So we started to look what is the properties of the material around it. Let's just simulate the cooling down as a physical process, so we can extend the data that we have to the whole cycle, and add this cooling phase in between so that we have enough data for training. And then we had one cycle where we actually made sure that our sensor is always plugged in. And when we did that, we noticed that the physical model and the mathematical approach is good enough at capturing this cooling down phase. So now we were able to use the old data as well to also better understand. So that's why we noticed why the process is working and why they can actually like shorten the time in the autoclave and other ones, because this cooling phase is one of the major contributors. And we were also able now to do predictions and saying like, okay, we can train our model on these 44 cycles to make predictions for the next ones. And there we are again. So that was then the result. Important is we only had 44 different production cycles. And so that means we couldn't use the deep learning, as I said before. Also, in these 44 cycles, there was a large variation in process parameters, because they were still setting up their process, still understanding what they want to do. So they changed a lot. So there was a lot of variation already to work with. The ground truth is this kinetic model based on DSC measurements beforehand. So after we observe the whole process, we can actually calculate what happened inside. And the prediction is done with something that's called auto-regression with a random Fourier feature kernel. If you're interested in that, you can ask some questions later. I'm very happy to talk about it. And yeah, so prediction inputs are always observed, and we get the temperature and DA data to make our prediction over time. And for us, important was when is a good time to actually make some changes, to actually say we are good enough. So we noticed after 30 minutes, the process is very slow at the beginning. We are not very good at predicting it, but starting the 40, 50-minute mark, we're actually very close to the end result as it is supposed to be, also for TG. So that was a good point where we said, after this time, we are very certain that our prediction is close enough so that we can make changes and also tell you how the rest of your cycle is going to be.
And Phil, what technique do you use for the prediction model?
Yes, so the technique is actually the idea we take always a little out. So we cut out a little part and we kind of move forward. So we always predict the next time slot and then the next one. So it's slowly building up. And this is this auto-regression. So we always make a regression on a certain number. That's why it's called auto-regression of inputs from the time to make the next one. And then it always propagates forward. So that also means that the longer the process is, the more inputs we need at the beginning to be sure that we are stably doing our extrapolation. At the end, that's what we're doing. We extrapolate from the start to the end.
Okay, thanks.
Good. And yeah, what was the outcome? So feedback to technicians. They can use the web app and they can see trends in the cloud. Also, of course, here was the analysis very important. We also able then to record for different composites, how it's going to behave, how you can do it. We have the flexible cycle times, especially now in this example. We also have some customers which have a lot shorter cycle times, like only a few minutes, because they have different materials, where we are also able to say, like after 30 seconds, okay, you need to adjust your cycle time, extend it a little, or maybe you can shorten it to have your parts actually removed earlier and without having scrap. And yeah, that's also then the last part is, of course, the scrap reduction. If you are able to see beforehand that you might need a little longer cycle, so that you don't have scraps. That's good. If you see you're much earlier finished, then you can stop earlier and save energy. And that's usually what the positive outcome is. Which industry are we working with? Which one is already using it? We have automation, of course, aerospace, building and construction, renewable energy, always a big part right now, electrical applications, also insulation of the electronics, yeah, consumer goods, but also military defense. So everything that's connected somehow to plastics and one way or the other is already interested or is working also with some of our technology. And with this part, I'm very glad that you made it to the end, and we can start our Q&A session.
Thank you very much, Phil and John, for the great presentation. So as the slide you can see on screen, it's now time for the Q&A with Phil and John. So if you have any question for them, it's time to post it in the question tab. And I see that we have already a few, so thank you very much for this. So let's start with the first question, a question that I wanted to ask to John during the dielectric analysis part. I'd like to know what are the limitations of dielectric analysis.
Thank you, Benjamin. So, of course, since here we are using an electric field and measuring what's happening with inside the material as did electric field trials, highly conductive materials can be an issue in the electrics, because then this can cause a polarization and can cause noise in the data. So if the data is not good, the solution at the end is not going to work. But so what we did, if all of you remember our sensor in a simple way, there was the outer electrode, the shell with the thread. Then there was a wide as cylinder, which was a ceramic component dividing the electrodes. And then in the inner electrode, then has a proprietary code. This is a code that reduces this polarization for perhaps all of you carbon fiber, really highly conductive material. So that's one of the biggest challenges that we noticed with our customers, and we were able to solve it by troubleshooting this using a proprietary coding. So now this inner electrode filters a lot of this polarization, and our data looks great.
Thanks very much, John. Let's move on to the second question coming from Ahmed Inamdar, who has two questions, by the way. The first one is how much parts area one dielectric sensor cover?
I can take this one, Benjamin. Thank you so much, Ahmed, for the question. So there are two parts. A lot of our customers are concerned with quality control and surface finish. So for that particular part, we have sensors with maybe a diameter of a couple of millimeters. I'll say up to 8 millimeters. Sometimes we might want to cover a little bit more of surface. So this there is another sensor which will be up to maybe 15 millimeters. We will definitely have a little zinc mark like. If some of you are familiar with injection molding, it's kind of like an ejector pin like mark. But because our sensors are so small, most of the times this doesn't affect the surface finish of our customers. Or if it does, then we normally place the sensor in a location where there will be a secondary operation, perhaps drilling a hole. So that's the question for that, a couple of millimeters. Yeah.
I think the second part is probably for me. It's how the degree of cure was correlated to the dielectric plot. That's something I'm working on, and currently that's usually depending on the material. So each material is a bit different in how it relates. And what I'm using for modeling this one is, of course, the ion viscosity and the heat. So the example you saw is a very nice example there. It is not so difficult. You can just have some sinus curves at certain points to just intersect, and then you can scale, but most times that's not as simple. So we have a little bit more complex model that is partly physical related and partly has a mathematical black box inside, which is able to work on more materials to give us this relation between the degree of cure and the ion viscosity. One important part maybe is they will not perfectly match to the one from the DSC because we're measuring something different. So while the behavior and the trend is very similar, you will not have a perfect match. You could always make a perfect match, but then that's just wishful thinking. So we're going to measure in the part directly, so it usually should also look different than the one from the laboratory, right? Because the one is a measurement from the laboratory, the other one from the machine.
Thanks very much to you both for those answers. Next question is from Sadi Bose. Can the data obtained from this sensor be correlated with information which can be secured from scanning of the final composite part by using machine learning? And if yes, how?
Yeah. Again, I will take this question. So yes, it can, and actually that's one of the parts that we like to do. So why at the beginning, especially for the forecast, we can rely on these kinetic models and on laboratory information. If we have process where there's changes, also change the material, there might be some pre-steps included that the laboratory cannot capture. If we get feedback afterwards, like, is the part good? Is the part not good? Is it undercured? Is it brittle? Is there some surface issues? If we have this one as labels, also the parts that are good, we can use this information to actually adjust and relearn our models to be more accurate to what is happening inside. So we do this via retraining of our models to include information that the customer can provide later on.
Thank you. Let's move to the next question from Jack Davis, who is asking, in addition to monitoring the cure cycle, do you also use the dielectric sensors to detect resin arrival for the purposes of flow front tracking? Has this been successful in terms of reducing scrap rates too?
I'll take this question. Jack, thank you for the question. The short answer is yes. So depending on, well, our team will work with the specific case study. Depending on the length of the part, we can position different sensors in different locations. And as we saw as in the visualization of the plot, we can, within this resistivity or what we call ion viscosity, we can see the minimum viscosity point. This will be very important for flowability. So then once you have that information, you can actually adjust different processes like temperature. And we have done this, of course, in this case study, there were one sensor at the beginning of the part, one sensor at the end. The sensor is will be in a high quality criteria area where there is a suspicion that the flow from might not reach. So there it will be very easy to know, did the resin reach that part? If it didn't, what happened? And with the prediction of the flowability, one can adjust things. So we make sure that the resin reaches the end of the mold before gelation takes place.
Thank you, John. And Jack Davis has another question. Is machine learning only useful for large production quantities since it requires a lot of training data? Do you have experience of using machine learning with synthetic data prior to actual production?
Okay, so two parts again, I would take this question. The first part, I think, was already answered in this talk. Machine learning is able to work with few data. Then you just have to choose appropriate method like we did, so not use deep learning. In fact, it's actually one of my specialties to work with productions where we do not have access to large amount of data and where we cannot do transfer learning. So we cannot use data from somewhere else, either because there is no available or someone doesn't want to share, and then have specific models working with this very few data points. Yes, so second part is a yes/no answer. So we do have some experience with synthetic data. And in a way, also our example was a half synthetic data, since we had to model something, a part of the process we don't have. The difficult part is, so let's say we have some measurements, then we can multiply these amount by using information, noise information to generate new samples. So having a synthetic way of boosting our information. That's something that is possible in our process. It's all right. We don't use it too much actually, since we don't see as much improvement. There's a better way to do it. Only working on synthetic data for plastics, we have not done yet. And I am not sure if the real, like only model data is actually good enough for doing the machine learning. If that's the case, we could also just use the model directly. So that was used to generate the data. I have done it before for some other process using different kind of sensors. So it was infrared sensors. And the problem is that you usually are not able to foresee all kinds of noise. So even you can do it to have a first idea, if it is possible, you cannot use these models in productions, as they're very prone to be affected by any kind of noise that you haven't seen or haven't modeled before. So I would really not advise to use machine learning models only trained, pre-trained, okay, but only trained on synthetic data, at least from my experience, is not a very stable solution.
Thank you. And we have a very last question from Marez Ait Mohamed, who thank you for the presentation first. And he's asking how much is roughly the amount of required data to run a reliable machine learning analysis. Let's assume we've got data regarding residual stresses somewhere in the parts.
Yes, very difficult question to answer. I had examples where we were working with 20 samples, and we were very, made very robust models that could be used in production afterwards. If it is about detecting cracks in surface, detecting stress parts, from my experience, the issue is you might probably have a lot of very good parts and only very few of the parts that have this specific error. So the question would be more, how many good and bad parts do you need? You can either have a large amount of very good parts and just train to detect if something is good or bad. So just say like, I have something that is good, I have something that is bad. If you do that, you might be already good with something like 100 to 200 good parts and only 5 to 10 instances of errors. If you want to know exactly where the crack is and what it is, you would need a lot more data. Surface cracks usually goes up to 1,000 in my experience, but that's something that was done with image processing, not with our sensors. So I'm not sure, honestly, how many we're going to need, but if you really want a localization of it, I would assume it's going to be quite a lot of numbers. I mean, if you talk about 100 to 1,000, it's still very limited data compared to the data that's used in the very big models. But yeah, hard to say without seeing some data, honestly.
Thank you very much, Phil, for your answer. As we reach the end of the webinar, I'd like to thank all the participants for joining us and for your insightful questions. If you have any further inquiries or wish to continue the discussion, please don't hesitate to reach out to sensXPERT using the contact detail provided on your screen. A special thanks goes to sensXPERT and everyone involved in making this webinar today. We appreciate the great presentation from Phil and John, as well as the contribution of Carly, Jean, and Milena in organizing this event with JEC. Rest assured, this webinar has been recorded and you will receive an email shortly containing the link to watch the recording and to download the presentation. You can also find it on JC Web TV, on jccomposites.tv, where you can, of course, access to all previous webinar, exclusive video content and interviews, as well as conferences from JC events. We look forward to having you again in our upcoming webinar. Thank you once again very much, and until next time. Bye-bye.
Bye-bye.
Bye, everybody.